This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Degrade the, but how would it degrade the performance? Noise. I wouldn't. And the other thing I try to be careful is when we're going to talk a little bit more about this today. When we talk about noise, we're going to talk about noise as being something that's stochastic and something that you can't predict. Here we're talking about something called distortion, right? So the distortion. So what were you going to tell me about the distortion? So you get into okay. So you get into the modulation of products, which means what? Well, yes, but what it means is if you've got two when they're talking about intermodulation, if you've got two sinusoids, what it's saying is those two sinusoids are actually mixing. Right. That's what intermodulation means, right? So therefore, if you had sine theta 1 of, a sine of a particular frequency, say theta f1, and then you had another sinusoid of frequency f2, you're going to start getting the sums and products and sums and differences of those frequencies. Okay, interesting. But why do I care? What's the significance of all this? And which ones do I care about the most? The order.
The order. 2f1 minus 2n, 2f2 minus. These two are in them.
Okay, perfect. Okay, so what you've got is you care most about the third order intermod products, right? And that's when it's 2f1 minus f2 or 2f2 minus f1 because they appear in band. And that's an issue why? Yes?
Because it's hard to filter them afterwards.
Yeah, you can't filter them. They're in the band of interest. Right, exactly, right? How about 2f1 or 3, if it's 3f1 or 2f1 or whatever, why don't I care about those? So you can filter them, sure. They can be challenging sometimes to actually filter them, right? But you can filter them narrow out of bands. Okay, fantastic. All right, so, and then you would have gone through and we talked about P1dB, or you would have talked about P1dB, and then there was an IP3 number, right? So did you just talk about IP3? I'm sure you did. It's third order. Okay, so it's IP3, right? What's that? What does that mean? And who cares? That's a definition, right? But who cares? Yes, it's not working.
Oh, it's an excellent one.
I tried doing that.
For an excellent one, isn't it?
Alright. Yeah, so it's a third order intermodulation product, but what does IP3 specifically mean? Okay, so you're on the right track, very close. It's the point at which the IP3 is the point at which the third order harmonic is in the same size as the fundamental. What's dynamic range? So you had IP3 and then you also had dynamic range. I'm sure you must have described or discussed dynamic range. What was the name?
Between the nose level
And the second, okay, yep. And but what happens to the dynamic range? And if I don't have any intermodulation products, IP3 is noise, and then the height of the range of the signal. So that gives me my dynamic range. What happens if I've got intermodulation products? Do I have to take that into account? It grows faster, not
Yeah, it grows
faster, right? Okay, and it grows 3 times as fast, right? But I guess what I was trying to say is when you're looking at dynamic range, you also have to look at incorporation, right? If you don't have any noise, you could just say, my noise scores from my signal level, power level, those sort of range, I've also got modulation products, I've also got to take that into account. Right. Now, let me see what else. You went through dynamic range with noise, intermodulation products. And you talked about spurious-free dynamic range. The other thing that you talked about was what happens when you have a cascade of amplifiers, and what happens to those amplifiers. Can you please explain that to me? Why do I care about it? And why do you care about it? Or why should you care about it? Can you give me an answer? No, really sure. Okay, no problem. Anyone else? Anyone else? Do you want to give me a try? That's it. No, it's okay. No problem. No problem. Just a pencil. Okay. I'm not quite sure. What was the question again? We said about. Sorry. Oh yeah, if we cascaded amplifiers, why do we need to care about the overall IP3 number? What's its significance?
It gets amplified through the system, so the initial amplifier is the most sensitive. It's the one that you want to put in next.
Right.
The greatest range. But the last amplifier is the least important one, or the easiest one to design.
Right, because you got it goes the other way around. Yeah.
Something a bit of confusion. I think the terminology that Class used about IP3 is different in the notes. I call it IM3.
All right, he might have used line.
Or maybe he used IP3. I can't remember.
Okay. All right, let me, I can't remember what the terminology was, but essentially what we're showing is that it allows you to actually work out how the IP3 varies through the system, and what it shows is that as you move forward, that it's the first amplifier that affects your IP3 the most. So therefore, what you're trying to do is, as you increase the cascade, it actually makes your IP3 numbers worse and worse and worse, right? So you want to avoid that, right? So yes?
Pretty sure we said the opposite, like the last amplifier was the most important.
Yes, your definition, okay, I've got the definition of, yes. The noise figure, yeah, okay. Yes.
The IP, and apparently he told us that for the noise it would be
The first.
like, yeah, exactly.
The first, yes. I was looking at the definition. Yes, so it's the last one is the most important, and as you're going back, it has less and less of an effect. Whereas for noise figure, it's actually the first amplifier which has an issue. We'll describe that. Did they fix it? Sorry? Yes? No? He's outside, is he? Oh, okay. All right. So that's what we did last week. Now, I guess you guys can actually see your notes, right?
Yeah.
So we might as well do it that way. Otherwise, we'll miss the whole lecture. Okay. So what I wanted to talk about today was going to go on from distortion and start talking about noise, right? And specifically, we're going to talk about how do we calculate noise in active circuits. And I guess what I wanted to talk a little bit about was, well, so far, what have we learnt when we're designing a system? Well, we've said if you were designing a power amplifier, well, the very first thing that you would do is you'd look at its stability, and we worked out how to do the kappa delta test in order to prove stability of that particular amplifier. And also we stated that if the system was not unconditionally stable, what it meant was that there were certain regions in the Smith chart where you could actually have a source or load impedance which would cause your amplifier to oscillate. And specifically what we did there was go through the process of determining the stability circles, right? So if we had your input and output stability circles, right? And we went through all that. And after that, what we've done is we went through and said, well, provided that the system is stable, what we're able to then do, or we know where the regions of stability are, we went through a sequence of processes in order to work out how to determine the gain and maximum gain of that amplifier. Right? It was, in this particular case, we're talking about a single stage amplifier where we were looking at, we had a transistor which had a particular set of scattering parameters. How would we design the input and output matching network in order to get the maximum gain or some other gain, right? And we went through the process of going through, and designing those networks in order to be able to determine the optimal source and load impedances under, unilateral assumption, and then what we also did is if we didn't have that unilateral assumption, we could do a bilateral conjugate match, but under those circumstances we said, well, we can only do that if the system's unconditionally stable, and we went through the process of working out what we specifically needed to do under those circumstances. So we worked out about how do we work out gain, how do we work out stability. Let's talk to you a little bit about intermodulation products and distortion. And we went through and talked about, and no doubt went through and talked to you about the significance of that, which included that you've got products, if you've got some kind of nonlinearity, the third order harmonic actually appears in the in-band, you can't put it out. But the other issue is that the nonlinearity also causes you to have output signals, especially in RF, which you might be transmitting in regions of the spectrum that you're not allowed to transmit, because the regulator says at these particular output frequencies you must your output signal must be below a certain level.
We're trying to reset the whole thing.
Now today what we're going to talk about is noise, right? So what is the difference, and I just want to make sure that you're all familiar with, what's the difference between noise and distortion? We talked about it a little
You can only
bit
see the input.
just when we started off here, but can someone tell me what do they believe is the difference between noise and distortion?
It's always exists.
Well, noise always exists, right? Yes, and distortion doesn't always. Okay,
Even though
I can live with that. But what about being able to predict noise? Distortion, I can always predict distortion. If I had measured my power amplifier and I worked out its transfer characteristic and provided that the operating conditions of that power amplifier did not change, like for example its biasing conditions and its temperature didn't change, if I put a particular input in, I would definitely know what I would expect the output to be, right? What about noise? It's random, it's a stochastic process. So you wouldn't be able to, even if I knew what the noise waveform was, a second ago, I couldn't tell you what the noise waveform is going to be in the next second. I can actually tell you what I would expect its mean value and its standard deviation to be, but that's the only thing I can say, right? And so what we're going to do today is talk about, well, how do we look at noise, how do we quantify noise, how do we then design how do we go through the process of actually designing an amplifier stage so that it has certain desirable noise characteristics or noise outputs. And what we're also going to do is going to define noise figure or cascading noise figure and the like. Maybe what I'll do is I'll be holding my notes so that I can actually remember what I'm supposed to be saying. Now, what causes noise from an intuition? Yes.
Like everything around
Everything. But what are we, okay, so everything causes noise, including this lecturer who's talking a lot of noise at the moment. But in an electrical system, what is the physical mechanism? What would you think some of the physical mechanisms are? Electrons. Well, what about the electrons? Sorry, there's a couple of things. No, that's okay. No, I'm listening. Okay, so essentially what happens is...
I'm just going to repower it.
Yes.
Okay, it needs to repower. The computer may go off.
It's okay, no problem.
Okay.
We're trying our best without it at the moment.
Yeah.
Okay, so what happens is, essentially, whenever you've got electrons and it's not absolute, and they're not at absolute zero, which is 0 Kelvin, these electrons are actually wiggling around, right? And they have a distribution of velocity, right? They're not all going at the same speed, they're all wiggling around. Some of them have got more energy than others. And essentially what happens with these electrons is they, as they're wiggling, they actually are smashing into how do you call it, into the lattice of metal or something. And that's what actually gives you the noise, right, in a resistor, for example. But you can also get noise when you've got a radio signal going through a gas, right? Because it's the same type of effect, right? So you've actually got these radio waves, interacting with these molecules, and these molecules are doing, they've got a whole bunch of distributions, and they're affecting what's actually happening with what you're actually receiving at the receiver. So, as you pointed out, noise is quite fundamental, right? So therefore, you can get background noise. And I assume you're going to tell me something about background noise, especially since you've got your NASA and Apollo 11 shirt on. So if I pointed my antenna to a part into the sky, which we thought was very dark and whatever, would I expect it would be receiving a signal? No, but what I'm saying is if there was no signal there wasn't a star or something, and what you would do is you would still receive, background radiation, and what you would find is that background radiation, and I forget the experiment that these people So I don't know if you've actually gone through that before. With that?
I think so. Got the screen up here. Let's
All right.
start. Okay.
Okay, so, all right, so here, when you're actually been working out the Fourier transform, in order to work out the power spectral density, what the other thing that you need to do is if you've got a stochastic process, you can't actually take the Fourier transform of a stochastic process. It's not defined. You've got to do something called the Mato integrals and the like. So usually what you do is in order to work out what the power spectral density of a noise function is, you work out the Fourier transform of the autocorrelation function. Does everyone know what an autocorrelation function is?
Got it up and running. So it's
No. So you correlate two functions, right? So essentially what you're doing is you're trying to work out, it's almost like covariance, but what you're trying to do is you're looking at how close, when are the two functions correlated with each other, right? And if you think about it, if you're looking at a delta function, the only time that it's correlated with it, what it means is, in order to get a delta function, what it means is that the function has to, the autocorrelation function is such that it's only, the current sample is only correlated with itself. It's not correlated with any other sample. That's the only time you get an autocorrelation function, which is a delta function, right? So the only concept here that I just wanted to point out is power. In order to calculate power of a signal, you work out its Fourier transform. That generally applies for a noise process, but for a noise process, in order to be able to do it, you have to work out the autocorrelation function first. What I'll do is I'll put some noise or some notes up on LMS for you. Okay. Now, so what we've got is the power in watts for any kind of structure is related by KTB, right? Now let's now look at a resistor. Okay. And what we want to do is work out the noise model for this resistor, right? So what we're able to do for this resistor is, well, we know that the power, is equal to, V RMS on 4, right? So therefore what we can do, this is the equivalent noise, voltage, the power written in terms of voltage. What we're able to do is now rewrite, there's an R here, sorry. What we're able to do is now rewrite the power in terms, we equate this power with the voltage KTB there, and what we're able to do is now work out an equivalent noise voltage,
No, on the switcher.
right, which is just PNRN, right? So therefore what you can actually do is actually just show that this is 4 KTB
Which one it is?
Okay.
But the fact that
So what that actually tells you is
it's not anything.
if you've got a resistor, or a resistor at a particular temperature, you can actually work out what you expect the RMS voltage of that noise source to be, that resistor. Right. Now, very simple example. Okay, so suppose we've got dBm.
Yeah, it's 370.
1 milliwatt would be 0 dBm.
Computer.
Right, 1 on 1 is 1, 10 log 10 of log 10 of 1 is 0, right? So it's 0. Okay, 10 milliwatts. No, 10 log 10
Probably
is,
this USB because it should be coming out
log
with the
of
range.
10 is 1 times 10 is
It should
10.
be coming out with the tablets.
All right.
So it's not coming up. So it's still.
All right. Okay. So 10 dBm is 10 milliwatts. Okay. 0 dBm is 1 milliwatt. 10 dBm is 10 milliwatts. 20 dBm, just for, and I'll stop there, is how many milliwatts?
So the thing is, you really find out where the USB-C cable goes to.
100. Okay. All right. Okay, good. All right, good. Now, so the important thing here is if you've got minus 137 dBm, you've got to convert it into watts, right? So, okay, so yeah, what you need to do is convert it into watts, and then what we know is Vn RMS is equal to 2 Pn in watts, right, times the resistance. Okay, and when you do that, you'll find that the the voltage that you'll get, the RMS voltage that you'll get, is roughly 12.6 milliwatts. I apologise, guys. I'm sorry, but it's in the notes. I've got it in the notes also, right? So, okay. Now, the next thing that people usually refer to or talk about when they're talking about, resistors and noise sources is this concept of equivalent noise temperature. So usually what you do is you can think of it as if you've got a white noise source, you can actually say, you can model it, as we said, by a noisy resistor at a particular temperature, right? So we know, for example, if we had some kind of noise source, suppose this is a power amplifier, right? And we said that it had a noise power of, I don't know, 1 milliwatt, right? So I guess all I'm saying is we know that this relationship holds, right? So suppose somebody told us what the power was. What we can do is we can say, well, this amplifier, this component can be modeled as a resistor that's at this temperature, TE, right, where TE is chosen such that it gives us the right power value. Right. That's the concept of equivalent temperature. Now, the other thing that I wanted you to all be familiar with was the concept of noise figure. Okay. So essentially, when we have an amplifier or some kind of active circuit, or even some passive circuit, what happens is usually you have noise at the input. This device actually generates a little bit of noise, and your noise at the output is the sum of the noise at the input multiplied by the gain by this device plus whatever noise this device produces, and that's your total noise power, total noise per hour. And what I wanted to do was actually define this concept of a noise figure. And noise figure is essentially, what we're defining there is how much extra noise do we get, or does this device actually increase the input noise? Alright, so essentially the noise figure is defined as SNR out, I got this right, on SNR, okay, no. Okay, because SNR degrades and you want if you do the calculation, it turns out to be right. So it's, the noise figure is the ratio of SNR in to the ratio of SNR out. Right, and what you can actually show is because SNR is always, degraded, or SNR out is always less than SNR in, that actually tells us that the noise figure is what the noise figure is. What's the minimum value that we would ever expect the noise figure to be? 1. Okay, so the min is 1. Okay, excellent. And the max? Okay, all right, okay, good.
I guess it's written.
Now, one of the things that causes a lot of confusion is you've got a lossy network, a resistor, or an attenuator, right? What is its noise figure? Right? What is the noise figure of an attenuator or a lossy network? Now, what I've gone through and actually derived for you is how to actually calculate the noise figure of a lossy component. Okay? So, for example, if I gave you an attenuator, right? So usually what happens is in RF systems, you've got not only do you have active components, sometimes you've actually got passive components, right? And sometimes these passive components actually have some loss, right? And it could be something as simple as an attenuator, it could also be something as simple as a splitter, or it could be a piece of cable, right? So usually what you can actually show, especially when you go through this calculation, is that the noise figure goes as 1 plus L minus 1 T on T naught. Okay, finally. Okay. All right. Success. Even though the lecture's almost finished. Okay. So what we're doing here is we're going to go through the process of working out the noise figure of of some kind of loss, right? And it's absolutely key that you're familiar with this, because the issue is that whenever you've got RF systems, there's always passive components in there, right? And those passive components, without exception, have some kind of loss, right? And they, as we'll show in one of the examples, that impact your overall noise figure of your system, right? So therefore the question is always, what is the noise figure of a loss, of a lossy system? And it could be, as I said, an attenuator, it could be a splitter, or it could be whatever, right? Anything that's got some kind of loss associated with it. And what you can do is you can go through the calculations, work out what the power of the noise is, and what you can actually show is that the noise figure goes as 1 plus the loss minus 1 T on T naught, where T is the actual temperature and T naught is the reference temperature. And usually what you do is the temperature and the reference temperature are roughly always approximately the same, especially at how do you call it, at room temperature. And what you're able to do is to show that for a lossy network, your noise figure of of this lossy part is equal to L, right? So therefore, that's the noise figure of that particular component. So, for example, if I had a cable which had 5 dB of attenuation, what's its noise figure? 5. If I had a splitter which split the energy into 2 ways and I got a 3 dB loss in power, what's its noise figure? 3 dB. Perfect, right? So therefore the loss is equal to the noise figure of that component. All right? Now, what we're going to do next is talk about this cascade of networks and how noise is affected by, and the overall noise figure is affected by multiple components when they're put in one after the other, right? So what you can actually show is if you had 2 components, one had a noise figure of F1, the other one had a figure of F2. Let me draw this, it's probably easier. So if you had the following situation, right, and we said we've got some kind of noise here, and this is an amplifier that's got gain A1, figure F1, this has got gain A2, noise figure F2.
It's hard to see.
Okay. Yes, yes. All right. What you can actually show is for this network, the total noise figure is equal to F1 plus F2 minus 1 on gain of the previous stage. Okay? So this is the definition, or how you can actually go through and prove this for yourselves. This is how the noise figure varies as you've got a cascade of 2 elements. And what you can actually then show is if you've got multiple elements, you can iteratively apply this formula. What you're able to show is if you had, for example, 3 components and they had gain A1, noise figure F1, gain A2, F2, gain A3, F3, that the total noise figure goes as F1, F2 on gain of element 1, F3 on gain of A1 and A2. Remember, always in these formulae, including IP3, we're looking at linear numbers. Don't substitute the values in dB. It's not right. Okay? So what can we say about this relationship in terms of what is the most important, if we wanted minimum noise figure, right, how should we design our receiver? Okay, let me ask it a different way. Suppose gain. What can we say about the contribution of the second amplifier if the gain of the first amplifier is very high? What we can say is, because it's F2 on G, and suppose G is a very large number, and if the gain was 30 dB, what number should I put for gain? I gave you the answer before I asked the question, 1,000, right? So therefore, if you had, suppose the noise figure was 10 dB, so it's 10 on 1,000, this doesn't contribute much, right? So therefore, it's the first stage that contributes the most, provided that the gain of that amplifier is high, right? So when you're designing a receiver, what you should do when you're designing your receiver structure is try to build your first amplifier such that it has high gain but also low noise figure, because that's what contributes most to the overall noise figure of that transceiver chain. Okay? And what I'm showing here is as you're moving back, or you're moving back or forward, right? This is why there's always this confusion. As we're moving towards, if this is the first and this is the third amplifier, right, what is happening is, in this particular case, this amplifier has the greatest, provided the other gains are high, this amplifier has the highest contribution. Which amplifier has the highest contribution to IP3? Sorry?
Well, the IP3 is the last one.
The last one, okay. Okay? Now, and the reason why I'm drawing this out is because there's always a definition, which one's the first, which one's the last, right? So it's this, the one closest to the input, if we define that to be the first, then that has the highest contribution to your noise figure. And if we define this as being the last, this one has the highest contribution to your IP3. Okay, let's do a little example here, right? And the example is as follows, right? We say that an antenna is connected to an amplifier via a transmission line, and this transmission line has 3 dB of attenuation, and the amplifier has the following specifications, right? I need to correct my English also. And I say, well, the amplifier has 20 dB gain, it has a bandwidth of 200 megahertz, and an equivalent temperature of 145 degrees Kelvin. And what I ask you to do is to calculate the overall noise figure of the gain cascade. And what I'm saying is, from what's the noise figure, if this is the input, from here onwards. So the first thing we wanted to do is work out the loss of the transmission line. What's the loss of a transmission line? In this particular case, I said it's 3 dB. What's its noise figure? 3 dB. Okay. All right. Now, here I've actually done the full calculation where I'm saying it's 300 degrees Kelvin and whatever. Okay. So it's 3 dB. And its gain is, if its loss is 3 dB, its gain is minus 3 dB, and its gain, if I write it in linear, is a half, right? Okay, perfect. Now, when we're working out the noise figure of the power amplifier, it's just 1 plus T equivalent, in this particular case, because I'm using T equivalent on T naught, what we've said is the T equivalent is 145, T naught's 290, so therefore that gives me, this amplifier has a noise figure of 1.8 dB, which is a pretty good amplifier, right? Usually what I found in practice is it's usually hard to get to build an amplifier which has a 1 dB noise figure. I mean, you know, in radio astronomy, people go through a lot of work to get power amplifiers that have got like half a dB. Generally, the power amplifiers that you build on CMOS for, 60 gig power amplifier, low noise amplifiers, are usually in the order of about 7 dB, maybe even more, maybe even 9. So this is a pretty awesome low noise amplifier. Now, let's go through the process.